Okay, good afternoon. This is a first experiment in hybrid mode. So we have, I can't read, 20 plus people online and hopefully 50, 60 people in the auditorium. So we are also doing a new innovation with a camera which we have never tried, and that is complicated. It's feeding data to the computer that is projecting through the MS Teams, and it is reaching you. So it's So should I speak from there?
Monday to Friday online classes. Monday to Thursday online classes. कितने बजे से कितने बजे तक?
Hello. Okay, people who are attending this online, please turn their microphones off. Great. So welcome everybody. Thank you for joining us. This is, as I was saying, experiment in hybrid mode with a new device that we are trying with. So our speaker today is a little bit of a guinea pig. We'll see how it goes. As we all know, Technology Day is 11th of May every year. This is a day where we get a chance to honor the contributions of Indian scientists and engineers. And we also know why May 11th, because back in 1998, when some of you may be too small, the students here, but 1998 for those of us oldies was a great day because this was the day when India carried out the second nuclear tests in Pokhran. And we joined an elite club of 6 countries, which was called the Nuclear Club. And this was the test that was sequel to the first test that happened way back in 1974, which was codenamed, as some of you may imagine, will remember, was called Smiling Buddha. So the 1998 nuclear tests changed a lot of political dynamics, and the world started looking at India quite differently from then on. But it was also the day when 2 other high-tech events happened exactly on the same day. We had the first successful firing of Trishul, the surface-to-air missile. And also in the civilian technology space, we demonstrated the first flight of Hansa 3, which is, we are very proud that this was designed, fabricated, and successfully tested by one of our sister labs, CSIR-NAL. And this fully indigenously aircraft, which is built for surveillance, mostly pilot training, right, and reconnaissance purposes. In fact, some of you may remember that very recently as March 22nd this year, there was the Hansa, the upgraded version of Hansa completed the sea level trials, right? It flew some 100 plus miles on the sea, which is an important criteria for getting the DGCA approval. So that was completed. And in fact, Hansa NG, which is the upgraded version, also flew on the Delhi Janpath on the Republic Day. So we are very proud from CSR to have contributed to this. So the Technology Day was initiated by the then PM Atalji on May 11th, 1998. And the charge of organizing these events countrywide is given to the Technology Development Board. So they spearhead this process. And there are certain awards that are given in Delhi today. That function is going to happen at 4 p.m. And TDB also decides the theme for every year's National Technology Day. And in fact, the theme for 2022 is Integrated Approach in Science and Technology for Sustainable Future. And therefore, we have chosen our speaker very carefully to honor the theme for this year. So Vidyut Mohan is our speaker today. He not only embodies integration of science and technology, but adds another dimension to it, which is entrepreneurship. This is not just to develop technologies for sustainable future, but also to deploy those technologies for sustainable future, particularly for mitigating emissions, air pollution, and also at the same time providing sustainability to farmers. Very important reason for Vidyut to be invited here today is to inspire our young students here. Here is a person uh, of the same age as you guys are, and has become a very successful entrepreneur. So it's would be nice to hear his story. So Vidyut is a co-founder and CEO of Takachar. Takachar is a company, a startup that has developed technology for utilizing waste crop residues to make fuels, fertilizers, and specialty chemicals instead of course, burning them. The technology addresses, I think, in my opinion, a real unmet need of a very narrow time window in which burning of the crop residues happens very frequently today and causes all the air pollution in the Doab region, in Delhi as you see it. Vidyut is very decorated. He has received multiple honors and awards. He's the UNEP Young Champion of Earth Awards 2020, the Forbes 30 Under 30 Social Entrepreneur. He's the Echoing Green Climate Fellow. He's got the Earthshot Prize, the Mother Teresa Award for Social Justice, and another long list, which I'm not going to read. His company also has won many awards. They recently won the Social Alpha Energy Challenge Award, the Keeling Kerr Prize, the Massachusetts Clean Energy Center Prize, and so on. So very interesting company and a very interesting entrepreneur. So ladies and gentlemen, I present to you Vidyut. Vidyut, over to you.
Thank you so much, Dr. Lele, for the kind introduction. I, I, I don't know. I mean, if I'll play the role of inspiring everyone here very well, but I definitely look forward to engaging with everyone here and learning from all of you here with such rich scientific expertise in this institution. And I'd like to also thank Dr. Sarika for inviting me, and of course, Dr. Lele. It's a huge honor for me to be here in one of the most premier scientific institutions in the country, and interacting with all of you here. We ourselves as a company have benefited from the R&D ecosystem in this country, and obviously NCL is a big part of that, along with the startup incubator program through the venture center. So it's a really big honor to be here and talk with you all. Um, so today, my hope was I'll probably just talk about my journey till now, which started with a lot of chaos, confusion, trying to figure out what to do in life, and slowly and gradually how that unraveled um, to where we are now, dealing with a lot of failures and successes in between. But also at the same time, talk a bit more about the problem that we work on in our company and our solution. And would love to have an interaction thereafter also. So, yeah, if I think the slides. So essentially, as you might have read in the flyers, I co-founded the company Takachar, and I'll tell you a brief journey about how we started this and what we are doing and how we are trying to harvest value from agriculture and forest waste. Oh, yeah. Yeah. So imagine yourself to be a farmer. You're a rice farmer, and after harvest, you're left with 4 tons of rice straw on your plant on your farm, 1 acre of land, and you don't know what to do with it. The cattle cannot eat it because it's not very favorable for the cattle to eat it because it has a very high silica content, for example, or there's just not much cattle around in the area that you farm. Uh, and you don't know what to do with it. It's very costly to process it, maybe incorporate it in the soil and do other procedures with it. And at the same time, I have just a week to 10 days time to plant my next crop, which is say wheat. And I have this 4 tons of material lying in front of me and I don't know what to do with it. And I want to get rid of it quickly and cheaply. So what do? I'll probably just take a matchstick, ignite it on fire, and get rid of it. And when millions of farmers do that, not only in India, but all across the world, that leads to massive smoke emissions, that leads to deterioration of air quality all across the world. But also at the same time, it leads to contributes to climate change. And ultimately, through the smoke emissions, it leads to deterioration of human health as well. And it is said in some parts of India, the contribution of the open burning of agricultural waste leads to such a bad air quality, particularly in northern India, that it reduces the life expectancy of people in those regions by up to 9 years. Imagine that. So, that's how bad the air quality gets, and particularly in the months of October and November. And of course, this is not only a North India-based problem. It happens all across India in many other states, and even all across the world. And the numbers state that close to about 9 lakh crore per year of crop and forest residues is burnt in the open worldwide. So this can be rice husk, rice straw, sugarcane trash, coconut shells, pine needles, these kinds of agricultural waste. The value of this waste, right? If you value it according to what a power plant might on average pay for that waste, the value of that waste burnt is about 9 lakh crore per year. Now, imagine if this value could be shared among farmers and if they could earn extra income out of it, out of their own waste. And just another statistic, the open burning of waste in and around Delhi, for example, contributed up to 48% of the smog on November 4th, I think, in 2021. So that's how much it can contribute to the deterioration of air quality too. Yeah, so this is one of the photos that we took on one very smoggy day in Delhi. So it's right in the heart of the city in Connaught Place. So that's how bad it gets. This was in the morning. This was in the morning. So we all know burning of agricultural waste is bad. But we also know for a very long time, I mean, it's known that agricultural and forest waste, aka biomass, can also be used as feedstock for applications in many important industries. It can be used to make fuels, fertilizers, activated carbon, liquid biofuels. We've known this for a very, very long time, decades, in fact. So why isn't this scaling up to its potential? So anyone can guess? Anyone wants to guess or take a stab at it? Okay. Yes, I think you hit it on the nail there. The answer is that the current crop of technologies are typically like this: very large scale, centralized, capital intensive. And what that means is you need to transport huge quantities of uh, loose, bulky, and wet waste like this. That is very, very voluminous, right? Probably up to 50% or moisture content, basically transporting half of it as water, and that's very, very expensive to do. And there is a limit beyond which you can transport it across a certain distance. And that's why, because of this logistical constraint, the cost of transporting and processing this waste is what's acting as a limitation behind scaling of this particular field of waste utilization or renewable energy, if you can call it. So what at Takachar, what we learned is what we need to do is, instead of getting the waste to the technology, get the technology to the waste, right? So what we're trying to do is we're trying to develop small scale, low cost, portable equipment that can be just latched behind tractors and taken directly to farms and forests to process this agricultural waste into valuable products like fuels, fertilizers, or raw materials to make activated carbon. So essentially makes this loose, bulky, and wet waste into an upgraded, dense, carbon-rich feedstock in situ, which is basically valuable commodity product. But also, since you are densifying it in situ, it lowers the logistics costs from here on by up to 75%. So just going a bit on the I guess technology side of things, it's a very what was important for us to do was to have the machine designed in such a way that it can be set up in remote rural areas. It's simple to operate by semi-skilled or even unskilled people. It should be easy to service and maintain, right? If the machine is in a very remote part of India, the hardware should be serviced and maintained by locally available skill set. Local available people should know how to weld it there, or they should be able to grind things or drill things. So it's very important to have simple operations of repair and maintenance also. So what we've tried to essentially design is basically a tube like this, a vertical tube and a horizontal tube, and in which farmers dump agricultural waste into the machine. It undergoes this thermochemical process called torrefaction, which has its origins in French. And it was earlier used, basically torrefaction comes from the word of roasting of coffee beans to make coffee. Instead of roasting coffee beans, we are roasting biomass here. And what we're doing is we are heating biomass in insufficient amounts of oxygen and in controlled amounts of time. And what that takes out is these low energy containing molecules in terms of gases, and leaves behind this dense carbon rich material that can be used as a commodity product by farmers to sell it as a fuel, fertilizers, or other valuable applications. And what we essentially control is how fast we feed into the machine and how much air we supply. That's all. I know it sounds simple, but there is I guess a lot of automation and control within the machine that takes care of it. But from the farmer's end, that's all they need to do. Yeah. So where do we fit in various ways of handling biomass, right? So there are various pathways to handle biomass. So one is, of course, a thermochemical way of handling biomass, in which there are various kinds. One is, of course, gasification, where you maximize the gaseous output that comes from the biomass in terms of producer gas. There's combustion, of course, which you know. There's pyrolysis, where you maximize the liquid output from the biomass. So it can be bio-oil or biodiesel. Then there's standard mechanical treatment, where you just pelletize the biomass into a solid fuel by just extruding it through a machine. Then there is biochemical treatment like anaerobic digestion, where essentially you're going to use microbes to produce biogas, where you maximize biogas production, but you also get some manure out of it. And of course, we all know composting. So our process falls into the thermochemical aspect of things under gasification, pyrolysis, right? So you can call it torrefaction, though I hesitate to call it torrefaction and kind of typecasted that way, but you can call it torrefaction. And it's a thermochemical process where we try to maximize the solid output from the machine in terms of the char that is produced. So what are we doing essentially? We're taking raw biomass. So raw biomass, you can assume, would contain 100% of its mass, 100% of its energy, and 100% of its carbon content. It goes through this mild heating process between 200 to 350 degrees Celsius in controlled amounts of air and controlled amounts of time. It takes out these low energy containing molecules in terms of gases. So what are those essentially? So those are volatile species it can be vapor form of acetic acid, formic acid, furfural, etc., which ultimately when it cools down, it forms this tar. right? Which is a sticky, gooey material which ultimately hardens to the solid black component. It produces steam, of course, carbon dioxide, of course, carbon monoxide, um, and then some amount of methane and hydrogen as well. And then you have the solid char densified carbon content, or the solid carbon content that you get. That is still 25 to 85% of the mass, but more than that, it's 45 to 95% of the energy. So what you're doing is you're densifying the energy content. So you're taking out the low energy content containing stuff in the biomass and retaining the high energy containing stuff. So that densifies the energy content in the biomass. So the calorific value naturally increases along with the bulk density, of course. So the volumetric density of the biomass. And of course, in certain applications, what matters is the densification of the carbon content as well. So if you're making activated carbon, for example. So yes, so this is essentially what the machine is. And the key aspect of the machine is how we control the reaction within the machine. So it's very important for us to control how the quality of the output is produced. So is there, so the amount of air that you feed in and the amount of time that the biomass stays within the reactor leads to a temperature distribution. And that tells you what is the quality of the output that you get. And it changes various parameters, the calorific value, the carbon content, etc. Basically the proximate and the ultimate analysis values. And what that enables us to do is to create this customizable bioproduct design. So for example, this graph for a fertilizer application shows that how with the increasing severity of the heating process within the machine, how the electrical conductivity changes of the biochar, which is an important parameter of if you're applying it onto the soil as a soil amendment tool or a fertilizer. And we need to be able to control that because different soils have different characteristics, different crops require different characteristics. So the control of the reaction is really crucial in our machine more than anything else. And yeah, these are some photos of various biomasses that we have tried: rice husks, almond shells, wood chips. We've also tried coconut shells, pine needles, rice straws. Right. So now zooming out a bit from the technology now and just talking a bit more about our prototyping and hardware and what we've been building. So we started with a lab scale prototype here. Typically, many such equipment will be here at NCL itself. And when we started with this, we didn't know what we were doing, where this is going to be applied, what's going to happen. And this was a funded research, and it involved putting in biomass and figuring out what kind of biomass at different reaction severities produce what kind of quality of char, and then studying various parameters that you can do experimentally with it and model it and do everything, all the research out of it that is possible. But where are we going to apply it? We had no idea as to how we wanted to go about it at that point in time. And I mean, we also realized later that this was probably not the right way to start. Also, it is kind of hitting a hammer to a nail and then figuring out, you have the technology first and then figuring out what you want to do. So yeah, me and my co-founder finished our respective thesis and thankfully managed to get some good advice from professors and other people who were interested in getting these kind of things commercialized. And they told us, don't work on the technology at all for the next 1 year. Figure out who is this useful to, right? Who's going to pay for this? I know this solves an environmental problem, but who is going to pay for this? Do they care about the environment? Will they pay for solving for the environment? They're going to probably pay for solving a problem in their lives. So identify that problem. For whom is that problem important, and the value of that problem. And then based on the needs that you identify, develop the functional requirements of the technology accordingly. And then then scope the design and everything and then prototype after that. So for a year, no technology design happening. Just skipped all of that and became a field researcher, traveling to Uttarakhand, Punjab, Haryana, Tamil Nadu, Indonesia, Kenya, the US, and try to understand various agricultural value chains and see what are the trends that are emerging and what are the pain points and who our end user is, who's going to pay for this. Is it the farmer? Is it the small farmer, large farmer? Is it the government? Is it the industry? Uh, who's going to pay for this? And only then did we get to developing such a prototype after that. And we still didn't scale it up to the requirements that we found out. I mean, we just scaled it up for this. If this was a 2 kg per hour prototype, we just scaled it up 10 times for 20 kg per hour prototype, because we're pretty sure there's going to be 1,000 things wrong with the smaller 2 kg per prototype. And though we got a lot of science out of it, but as you scale and you engineer it, they're going to be the scaling of the problems is going to increase as you scale. So we wanted to engineer things in a step-by-step fashion. So we actually made a very simple version of this and just scaled it up 5 times with a lot of the needs that we learned from on the ground. So we got to know what is the cost limit that we have. We got to know things like, do we need to make the machine fixed or portable? We got to know things like, okay, which is our starting agricultural value chain? We can't target every agricultural value chain that exists in the world. We're just a small startup. So which agricultural value chain should we start with? And who is the customer who's going to pay for a machine? And why are they going to pay for a machine, right? When they're already handling their agricultural waste in a very low cost and cheap way. So this is what we built, and yes, this prototype failed miserably. It had a lot of problems with it. It didn't give the results that we wanted. In fact, it started giving out more smoke emissions than open burning of the waste. Yeah, there was a lot of issues with it, but we learned a lot. We learned a lot from this process, and we played around with it so much that 2 patents came out of this process, and we were out in the field in a very congested part of Faridabad, just outside Delhi, just rented a small testing space outside one of the urban villages in around Delhi. At that time, we could afford that. And we used to go there and test it out, and we used to have these gas masks on our face because we used to smoke so bad. And yeah, but I mean, we learned why it smoked so bad, that why it didn't work, and it produced the quality of the output that we needed. But of course, there were certain design limitations to this. And based on that, we now design a alpha version, that, as you can call it, which is shown by this photo, which kind of takes into account all that we learned from what we tested from that machine. And this has processed various kinds of agricultural waste, ranging from rice straw, rice husk, coconut shells. We're also now testing with mustard husks that we've gotten from some farmers in Rajasthan. And this machine now is meets all the functional requirements that we are aiming for to commercialize now with farmers. This is still not our final product. I mean, this needs to still be engineered. I mean, it needs to be made to look better. It has a lot of scientific instrumentation on it that needs to go off before it goes to customers. A lot of yeah, the design needs to be made more elegant. But I think through a lot of trial and error in 45 degrees Celsius heat, we're still doing it right now. In Delhi, we go there at 5 in the morning because it's hot right now, and test it out and get data out of it, and then think of design improvements and what to do and change. And this machine is completely powered by batteries and solar panels. So it consumes an average about 300 watts of power. So we're able to completely run it off solar panels as of now, but in the future we plan to use the waste heat from the machine and generate a voltage out of it to charge batteries itself to reduce the solar panel foot, I guess, the number of solar panels that we need for it also. And in the end, the vision is to make something like this, something very portable that can be just dragged by a tractor to a farm and taken and just process the agricultural waste there. We're almost there. The chassis that you see on which the machine is based is the chassis of a trailer that can be mounted behind a tractor. We've just taken out the wheels for our testing purposes. But this is very close to that. Yeah, I mean, the prototyping process, there were some mistakes. The machine ended up bigger than the chassis. So there are some design changes that need to be made on that front, but we're pretty close. So what we've also found in the initial studies that we did on the machine, that as compared to open burning of the agricultural waste, we are able to prevent up to 98% of the smoke emissions, basically the particulate matter, volatile matter, and carbon monoxide contents as compared to the open burning of agricultural waste. So in the left, if agricultural waste is just burnt in the open, typically the emissions would look like that. On the right, it's how it will look in our equipment. And yeah, I mean, we are designing the machine to have standards that cater to the emission standards in the most stringent conditions are demanded, particularly in places like California or Western Europe. So that's how we're trying to engineer the combustion process in the machine as. So as I said, we're trying to design the machine so that it is operated by farmers in remote rural areas. So design has to be very simple and the machine has to be very flexible. It should be able to operate a wide variety of agricultural waste, right? It cannot be that the machine is just designed for rice straw, right? And then we have to design a completely different machine for coconut shells, for example. So we're trying to design a machine that takes in various kinds of agricultural waste. But essentially the idea is to make the machine simple. So, you know, we have machine that operates at air. It takes in air, right, at atmospheric temperature. We don't require any heated special gases such as nitrogen, which usually acts as a heating medium in many of such reactors. We do not have any scrubbing equipment in our machine at the moment. We're almost 100 times smaller in scale and 100 times smaller in cost than many other machines like this, and can take in a wide variety of agricultural waste. But the most important thing that we realized is in our development of the product, it's not essentially the hardware itself, but it's the control of the reaction that happens within the machine. That was something that was the most important for us, to control the reaction so that we're able to take in various kinds of agricultural waste and produce the quality of output that is needed to meet various kinds of industrial applications, be it fuels, fertilizers, activated carbon. So each of them have a particular quality requirement, and our machine should be able to tune the quality as per those requirements. Right. So a bit on the application side. So what are we trying to do? So biomass and its uses are diverse. But what we are trying to do is we're trying to use our equipment to cater to the activated carbon industry, the solid fuel industry, fertilizers, and other specialty-based chemicals also later. And essentially what this looks like as a picture is that, imagine I'm a large farmer in the village. I own and operate the machine. I collect rice, I collect agricultural waste from farmers nearby, and I pay them for that. So they earn extra income out of it and they don't burn it. I then process this waste in the village into this carbon rich material. And then our company connects these entrepreneurs to these various offtake markets to ensure that they're able to develop a solid business out of it locally in villages itself. So one such application is fertilizers, right? And typically farmers in Africa and Asia pay 2 to 3 times the price of fertilizers because there's logistics cost of importation. And in the case of India, the government of India subsidizes heavily the fertilizers, as all of you know, and the government of India bears the cost of that in multiple tens of thousands of crores. So there's a cost that is borne to the importation of these fertilizers. So fertilizer production is currently incompatible with rural farming, essentially. So it's very large scale, centralized, logistically complex, one size fits all. And of course, that leads to challenges such as it's expensive, it's not customizable according to the local soil conditions and the crop grown, and overuse of it ultimately has led to soil degradation, which ultimately leads to food insecurity, right? So our idea is to use this decentralized technology to downsize fertilizer production and use locally available residues to make fertilizers that are custom tailored to the local soil conditions and the local crops grown. So what we're doing is we're essentially taking crop residues, converting that into this carbon-rich material through our machine, which is called biochar. Now, biochar has various benefits. One is, of course, it has a very high surface area, so it can retain nutrients longer in the soil. It does not allow it to leach out. It retains moisture in the soil for a longer period of time. So it technically requires less amount of water. And you can also control the pH of the biochar. And by controlling the pH of the biochar, you can also control the pH that you want in the soil. And that is required by the crop. So you can do various adjustments like that. And this biochar acts as a substrate or holding material to mix nutrients in it, organic or inorganic, and sell it as a fertilizer package product to farmers. And this is essentially what the model looks like. And this is how our pilot in Haryana currently is, where we're working with an entrepreneur in a village who currently rents out agricultural equipment to farmers. And we think our hypothesis is these kind of people are potential customer segment for us. They collect rice straw from farmers, convert that into this fertilizer product, mix this proprietary nutrient blend that is known to them, and they sell it back to the farmers. And what we see is that, of course, it leads to improvement soil health, but it also yields to an improvement in crop yields. And we've also seen through our trials in the past that it has led to 50 to 100% reduction in chemical fertilizer usage. Over and above that, through some of our applications, we have seen that we are able to remove 370 kgs per acre per season of carbon dioxide equivalent emissions. We're able to suck out carbon dioxide from the atmosphere, which was locked away in the plants. And instead of that going back to the atmosphere through open air burning or decomposition, we are kind of burying it in the soil where it stays for hundreds of years. And of course, we are also preventing 730 kgs per acre per season of carbon dioxide equivalent emissions. So we're able to fight climate change as well. So this is the photo of our pilot site in Haryana right now. This was taken in October. This is locally available rice straw that we collected. And at the smallest scale, one machine can support continuous production about two tons per day of fertilizers and can serve around 2,000 farmers in a 20-kilometer radius. And we've done this in Kenya before, where we've worked with where we've been selling fertilizer for a few years now, and that has scaled to about 5,300 farmers and has also broken even as a venture. And what we've learned is that at the same price that farmers pay for their fertilizer per hectare per season, they were able to increase the yields by up to 27%. And as a result, also the net income by up to 50%. And this is something that we're trying to replicate in India now as well. Yeah, so these are some of the impact numbers that we have. So we managed to create about 6 crore of added rural value livelihood, recycled about 9,000 tons of agricultural waste, and sequestered about 11,000 tons of CO2 emissions till now also. Now, another aspect that I like to highlight here and is gaining a hot topic right now these days with all net zero targets coming up, set up by various countries, but also by various corporations, is also carbon removal. Since this fertilizer process sequesters carbon in the soil, the biomass produces this fertilizer, and we're able to sequester this into the soil. So what we are trying to do is, through this act of sequestration and through this act of mitigation of carbon emissions, that we're preventing open air burning, and we're preventing a lot of the emissions from transportation and logistics. So we're mitigating carbon emissions as well. So what we're trying to do is we're trying to connect with companies like Microsoft or Total who have set up net zero targets and set up huge funds to buy carbon credits from the voluntary carbon markets. And the carbon credits for the voluntary carbon market fetch a much higher price than carbon credits for just carbon avoidance, right? So carbon removal based carbon credits fetch a much higher price. So we're trying to connect Microsoft and Total, who want to buy these credits, to our farmers who are sequestering this carbon in the soil. So the idea is that farmers sequester carbon in the soil, and we verify and track that. And based on that, that we calculate how much, essentially, how much of carbon that they're sequestered. And based on the pricing of the voluntary carbon market that we negotiate, the idea is that these companies directly pay these farmers to sequester carbon in the soil. And our calculations show that this can subsidize up to 50% of their fertilizer costs, which is going to increase the bottom line of the farmer significantly. So that is one application. Another application that we're working on is activated carbon, which I don't know if you all know. I mean, if you've seen your water purifiers at home, you'll have this carbon filter, which is basically activated carbon. It's used to purify polluted air and water streams. And 50% of the world's activated carbon is made from coal and wood. 50% of it is made from coconut shells. And India is one of the world's largest producer of coconut shells. And interestingly, this is a well-established industry that's been there for decades, and coconut shell-based activated carbon is a very known process. But what happens is coconut farmers give their coconuts to coconut oil mills. Coconut oil mills produce coconut oil, and in the process, coconut shells is generated. Then they sell those coconut shells to village-level charcoal producers. Now, what these charcoal producers do is they just dig a pit, dump coconut shells inside it, ignite it. And that leads to huge amount of smoke emissions, but also in the process of cooling the charcoal, they dump water inside it. And that water becomes black and percolates down to the aquifers. And that's also polluting the groundwater. So the National Green Tribunal and the Pollution Control Board has actually banned this method of production of charcoal, which is a raw material to make activated carbon. And as a result, there is a raw material shortage in the industry, and that has jacked up the price of charcoal. And many of these activated carbon industries are operating at 50% capacity right now. So yeah, so what happens is the technology that's available is either this really traditional method, which was a livelihood source for the villagers, but is banned now, or you have these really sophisticated plants that cost 3 crores, 5 crores that these people in villages cannot afford, right? So what we're trying to do is we're trying to work with these coconut oil mills so that they can directly process these coconut shells into charcoal without the pollution, so that this method, so that they don't lose their livelihood. But at the same time, the activated carbon industry, the value chain continues, and they're able to procure the raw material needed for it. And at the same time, the pollution is omitted. So yeah, I mean, this is how the charcoal is produced, essentially in various parts of Tamil Nadu and Karnataka and Andhra Pradesh, essentially pits, and you can see the smoke emissions that come out of it. Yeah, this is typically an activated carbon company that's based in Tamil Nadu that we have also reached out to in the past and interacted with. So these are really large plants, large conglomerates, international companies from Europe, Japan that have set up factories in India, but they procure charcoal that is produced in that traditional way. And yeah, these are some of our users that we work with, and their coconut oil mills, and their biggest pain point is that. So I was talking about pain points, right? So why are they our end user? So what we learned interestingly was that these coconut oil mills neither have control on the price of coconuts that they buy, nor do they have control on the price of the coconut oil that they sell. The price of coconut oil that is sold is controlled by some really large corporations who buy it in bulk, and the price of coconuts is just dictated by the domestic market and just the value chain beforehand. So many times they operate at 1% margin or even lower than that, or they operate at a loss if they just sell coconut oil. And the sale of coconut shells is actually what adds to their margin. So our idea is to essentially address that pain point of a very low margin that fluctuates, that is not in their control, to kind of add value to their coconut shells so that and convert that to charcoal so they're able to earn extra income out of it, and kind of that acts as a soft landing or their cushion to their coconut oil business. But also at the same time use the waste heat from the machine to dry copra, which you see here, which is a step in the process of making coconut oil. And currently what they do is they dry copra in the sun like this. So they put it on Monday and it takes till Saturday to dry. And what happens is on Monday, they see the price of coconut oil is something very lucrative. So they set it out to dry. And by Friday or Saturday, the price of the coconut oil will suddenly drop. And so they lose out on the price. So the time that goes into drying is a very uncertain period for them. So if they're able to dry faster, it's under their control as to when they want to sell the coconut oil and at what price they want to sell. So that's the pain point that we're trying to target with this customer segment. Yep. So that's an overall on the business case. So overall, in 10 years' time, we do aim to mitigate 1 billion tons of carbon dioxide equivalent emissions and prevent 75,000 tons of particulate matter emissions per year by targeting all these applications in solid fuel, fertilizers, activated carbon, biofuels, etc. But what I wanted to also talk about today was also, some of the takeaways from my prototyping process and what we learned. I mean, we burnt our hands in a lot of things, but I'd just like to share some nuggets on what we learned from this. And I think the biggest thing is what I talked about earlier, right? So stuff like this, hardware technology that involves a lot of science takes time and resources to develop. We've been at it for 4 years full time now, and probably 7 to 8 years part time, right? And still, we haven't commercially started selling our machines yet. Right, so that's the amount of time it has taken. So it takes time and resources to do it. And if we are a software company, for example, we would have probably developed an app or some sort of a website within 3 or 4 months, tested it out, piloted out, maybe start getting some revenues itself, and start going to market early. But for a thing like this, that you need to imagine what the R&D journey looks like 5 years down the line. It's really important to know what you are trying to build, for who and from whom you are trying to build. So we learned it the hard way that it's really important to invest a lot of time before you start an R&D to see what the real world application is. And for whom are you building this, right? Who is the end user? Who's going to pay for it? And then work backwards and do the R&D. And that has twin benefits. It'll save you a lot of time and money. And kind of give you a direction, but also at the same time, there's an emotional angle to this as well, right? When you connect to the pain point of a human being, a farmer, on an emotional level, it has a much stronger impact on how motivated you are to develop technology around it and solve the pain point for those end users. So for us, this was a big reason. Of course, the pain point of the end users, but also the environmental impact that the smoke emissions had on the health of people, I mean, my family and me included, right? So I mean, I suffer from a permanent allergy because of bad air quality. So just having an emotional connect to the problem that you're trying to solve made me personally understand my science better and made me very motivated to be curious and to see what skills I need to learn in order to develop this product. So I think that emotional connect is really, really important. So yeah, that's what I talked about here as well, right? Working backwards from the need and developing the technology. And then understanding user pain points and the scale of the problems, right? It's not just understanding for one user. You need to have an idea like how big is the problem? Can you make a viable business out of it? And then work backwards to develop the functional requirements of the product, because ultimately technology development when it's out of the lab is a question of design trade-offs, right? And those trade-offs are constrained by what the user wants and what the user can pay for. And it's very important that you're able to have a healthy debate within your team who's developing the technology to see, where you want to compromise a bit, where you don't, where you want to be absolutely perfect. So it's really important to work. That discussion cannot happen at all till you understand where the end application of your product is. The other aspect, particularly for machines like ours, is if you're taking 4 years to develop a product, how are we going to get user feedback? How are they going to tell us that this is something that they want to buy? Are we going to wait for 4 years, then go to them and ask them, is this something that you're going to buy? And then they tell us no. And then those 4 years of R&D money, everything goes waste. So how do we test it out in between when we don't have a fully functioning product yet? So what we learned is that we understood what subcomponents of the product were important to the customer and what they perceived as was what they looked at and what they perceived was important. We developed those subcomponents, which were fairly quickly to develop as compared to the entire machine, and then showcased to them and then got feedback. Or we made really simple prototypes like these, like out of 5,000 rupees, we made some batch reactors out of simple oil drums and did a pilot. This was in Uttarakhand that we did a pilot with pine needles and try to understand the unit economics of operations of it. What are the challenges with labor costs? What are the challenges with biomass collection and things like that? Or we even did things like we made fake flyers like this, right? We told them this is how our machine looks. This is how much it costs. This is the functions that it performs. I wrote something in the local language to connect with them and asked to get and got their feedback on various things, on various features of the machine. And that helped us confirm a lot of the hypotheses that we had regarding the design of the machine and the functional requirements. Other big thing for us, particularly for a hardware company, is we didn't want to, at least we were thankfully advised in this in the early parts of our journey, that manufacturing is a really important component of it. And we don't want to build a reactor that is going to bump up the manufacturing costs and then take away from the constraint that I talked about that the end user put in terms of costs. We don't want it to go beyond that ceiling. And we want to work within manufacturing capabilities that are there within the country and that are standard and that are fairly simple to adopt. So it's really important right in the beginning stage to involve manufacturing in your design process, maybe in your lab prototype itself when you're doing R&D. Think of how easy it's going to be to manufacture that, and how where are you going to get your parts from? What are the supply chain? What does the supply chain looks like? If you're going to get a part that takes 6 months to come somewhere from abroad, right? Maybe that's not ideal, and there are various other consideration and costs that come along with it. You have to consider things like how do I reduce the assembly time of the machine, which adds to the cost of the machine? How do I reduce the number of parts of the machine? Is it more cheaper to have various number of parts that are simple to manufacture, or is it more cheaper to have one part that is more complicated to manufacture, but reduces the number of parts, right? So these are the questions that have to be answered right in the beginning, because it's going to cost you a lot of money and a lot of waste of time if you're going to do it much later down the line. And very important, I think is the most important thing that we learned in a prototyping journey is know what your niche is, what of your team, what you're good at, and focus on that. And for everything else, use standard available components that are available in the market. You don't have to reinvent the wheel on that. People have engineered that, developed that, use that, take help of that, hire a company that has developed that and let them design that. But you focus on what your niche is, at least in the beginning. And this process, and this is something that I learned, well, not through my startup journey, but in my previous job, I worked in a solar company that was into and developed solar home system for off-grid households for rural Bihar, UP, and Uttar Pradesh. And what I'm trying to say here is, if you're ever in a product development project, I know we are all scientists and engineers here, but don't only have scientists and engineers in your team. Because the reason I say that is we typically scientists and engineers tend to think rationally, of course, but end users don't think like that. End users don't, customers don't think rationally. A lot of decision making, purchase decisions are not rational decisions. So, for example, this end user that I met during my job, this is a village, completely dark, off-grid village, and we were installing the solar home systems on finance in this village in rural Uttar Pradesh. And this customer was a very difficult customer. So I actually myself tried to pitch our product to them and tried to sell it to them. And there was a family of mother, father, and two children, right, that lived in this house. And I pitched them that at 5 rupees a day, right, you can have the solar home system that can give you two lights and a fan, right, and you also can charge your mobile phone. And you spend 5 rupees a day or on your pan or BD, right? Instead of doing that, if you spend on this, you'll have electricity for your children to study at night instead of polluting kerosene lanterns, right? And the response from them was, he asked me this question. So he put the question back on me, and he told me, after a very hard day of work, right? What do you do to relax? Right. So I said probably probably have a coffee or something in between work, or do something like that. So he said, "Jo aapka coffee hai, mera hard day through hard days labor of lifting bricks and stones, that pan or that BD is my way to chill my time, and that's where I'm able to be there to work every day also and are able to earn an income." And that's why I'm not going to give up on my BD or that pan, right? So my pitch was wrong. The way I framed my pitch to the end user was wrong, and so typically I would make a rational decision. I would buy this for the education of my kids so that they're able to study at night and do it. But not all purchase decisions are like that. Many of us buy many random things on Amazon and Flipkart these days, maybe, right? And they may not be always rational decisions. So it's very important to have an interdisciplinary team, having design thinkers, business people, people who understand supply chain logistics, and of course technical people also, who are able to identify these things and are able to feed into the design of the product. So yeah, that's essentially what I have at the moment. Would love to interact and answer any questions if there are. Many nuggets of learning in this talk. There's only one mic you can share. You can come here. Yeah.
Thank you, Vidit, very much. As I was saying, there was amazing nuggets of learning there that many times we working in our labs don't even understand them. Okay, and certainly if we don't understand them, we don't appreciate them. So I have many questions, but I'm going to leave it to the audience to start. Let this be a little more interactive session so that we can get the most out of Vidyut here. Gopi.
Right. Okay, so your question is around, I mean, even before I formally started working on the startup, how beforehand was the motivation behind getting into this field and working into this in the first place? Um, I mean, to be honest, I mean, when I was an undergrad student, I was quite confused to what I wanted to do, but I was pretty sure I wanted to um, do something environment and energy related. I knew I wanted to get into the environment space. I knew I liked mechanical engineering, topics in mechanical engineering. Uh, so that uh, so that kind of naturally led to this work in biomass. But I think what led me during undergrad, I did a lot of internships with organizations that exposed me to problems in rural parts of the country. Uh, so I interned with various organizations during that time, and actually I got inspired by the founders of those organizations at that point in time. And through their journey of how they were using their skills and knowledge, and then coming and then then working on this and then struggling and then persevering and coming about and then being successful after that, that was something that was I got to witness that, and I thought that was something really inspiring from those people, just from the impact that they were trying to achieve. I saw that it was really hard work, but when you actually go and meet some of the end users and you try to speak to them and what they say and what you hear from that kind of really motivated me towards social entrepreneurship and gravitated me towards that. So I think that played a very big role. And I also saw very successful, highly educated people who kind of came into this role. I think, just lucky enough at that point in time to be around a lot of these people as a student. Uh, and I saw that they were using their education and skills uh, for the right thing. To and They weren't doing it from a philanthropic perspective. They're still running businesses, but that business had a purpose. Uh, and yeah, I mean, those experiences just during my college time just said ki, I mean, it just made me really disinterested in the placement process at that point in time that was happening, and I found all the jobs that were coming my way, either IT jobs, which as a mechanical engineer I didn't want to do at all, or were jobs where I don't know if I'd get to do a lot of critical thinking and see what is the impact that my work is actually creating in a tangible fashion. Uh, so that was what I was in my undergraduate time. My upbringing also played a lot of role. I think my parents we just traveled a lot all over the country, and I guess did tourism in a way that exposed me to a lot of things that otherwise you don't get a handle of. In normal way people travel. So I think my parents are to credit for this as well. But the real thing happened during a master's program. I think during that time, I, I think I got sucked into this entrepreneurship ecosystem in this university. I think almost all of my peers were trying out some kind of entrepreneurship idea through various courses that they were doing, trying to see how inventions and patents that are developed in the university, how that can be applied in the real world. I think uh, I got just sucked into that, and I think that's and I try to marry my earlier experience of doing social entrepreneurship with this, and I think that's what finally led me to this path.
There's one question behind first.
Thank you, Vijay, for your inspiring talk. My question is that when you burn that crop in your prototype, gases like carbon monoxide, carbon dioxide, methane, and hydrogen. Told about carbon dioxide. What are you at present utilizing? Doing with methane and hydrogen. Are you destroying it or utilizing it?
So we're using the energy content in it and combusting that within the reactor to provide energy for the torrefaction process. So what comes out is most 99% carbon dioxide and steam. Yeah, I mean, depends from biomass to biomass. Yeah, I don't have the exact numbers right now because we don't. I mean, gas analyzer is an equipment that is expensive, so we don't have that with us. But yeah, what we are doing is we just do secondary combustion of the permanent and volatile matter gases to provide energy for the torrefaction process itself. So the entire process is autothermal. We don't need any external source of energy for the heating process.
Who is your target customer? The target customer decides the price point. And then the second question is the quality of biofuel you are producing with your equipment and the quality of fertilizers in already present in market. What are the differences? Because if what the product what your product is giving the fertilizers, fuels, and all these things, if they are not highly or they compare to more, then people will not use the product. I want your answer from. And sir, in Pune area, mostly there are so many nurseries around. So can we use grass, that garden grass also as a biomass?
Okay, thanks for your questions. To answer your first question regarding our customer segment that we identified, so various agricultural value chains are different. So we don't have one particular customer segment overall. So for example, in the case of coconut shells, we work with small coconut oil mills who are end users. With rice straw, our hypothesis is that it's people like these farmers in the villages who rent out agricultural equipment. So they rent out super seeders, happy seeders, other kinds of agricultural equipment, or they rent out baling. So they rent out machines that bale rice straws. So these are the kind of farmers that we are uh, testing out a machine with. Yeah, we are validating that, of course, through these pilots. The process of the proof of concept is to do that. But I mean, that's how we narrow down our user segment. So it's not one common user segment across every agricultural value chain. Coming to your second question regarding biochar. So biochar by itself is not a fertilizer. Biochar is a soil amendment tool by itself. So it's not going to provide nutrients to the plant to grow, but it'll amend the soil. And we custom tailor to the biochar needs to be produced according to what is missing in the soil. So we take a soil sample, we try to understand what's missing in the soil, what nutrients are missing in the soil, and then we try to tune the biochar maximum in a certain way that maximizes the deficiency of those nutrients. But biochar by itself is a holding material for organic or inorganic NPK nutrients that are mixed on top of it or after it once it's applied to the soil. And essentially that leads to an increase in yield of the crops. Grass can be used in our equipment. I have tested that in the past, but we haven't really researched into an application for the char produced from that yet in a lot of detail.
Asha and then Rakesh. Yeah, go ahead.
So when they're not using the machine, they can use the solar panel for other things also. The solar panel is a cost of the machine, but it's a minor cost of the machine. The cost of the solar panels has really fallen down over the years. We're also trying to reduce the number of solar panels that are required to operate a machine by simply using the waste heat from the machine and generating a voltage out of it, say through a thermoelectric generator, and then charging a battery using that, so that we're able to reduce the number of solar panels also, and that will make a machine less bulky too. So that's the idea.
There is a very the byproduct of this, that is a bio-oil that is. So are you thinking of bio-oil application, because there are applications?
So that is of course an application, but right now we're trying to maximize a solid material output yield rather than a liquid material output yield, um, because we think it's just as a startup, it's just faster to commercialize that, and for us it's really important to get to market first. Uh, I mean, of course, we from a research direction perspective, as you said, that's important, but that would take longer R&D effort on our part. But I guess that's one of the differences between, I guess, a research lab and a startup. That I mean, we do have to get to market fast so that we're able to generate revenues that are able to sustain some of the futuristic R&D that you're also talking about. So we think maximizing the solid output is the fastest way to market right now. So we're focusing on that at the moment. Yeah.
You see that as an urban.
It can be used for thermochemical treatment provided the moisture content of it is below a certain limit. Um, if not, it has to be dried first to get to that limit and then use it in the machine. Yeah, because otherwise you'll just be heating water for a long period of time just for the latent heat. And that's not going to be very efficient. But of course, then you can, once you've dried it, you can produce biochar out of it. We haven't explored applications of that as to where that biochar can work, but yeah, you definitely can.
I would really like how to see something else. If you tell your equipment 7 lakhs, but not wrong. I'm going to buy it. Train a normal like diploma. I can run this. I'm going to be a friend, and I'm going to protect edges. And understand some other thought. We can make it.
Sure, definitely. I think point taken. I think regarding cotton waste, cotton stock waste, I've received a lot of people from all over India have reached out to me regarding that, particularly in Maharashtra, Karnataka, and Andhra, and Telangana. Lot of farming communities have reached out to me regarding the burning of cotton waste. So that's something that we will be looking at for sure. And yeah, I think by July end we should have our machine on wheels. That's the beta version that's being built. Yeah.
You got a customer there.
Yeah, I'll take a number.
Take his number. And, yeah.
Yes.
Yeah. No, go ahead. Go ahead.
Application of
So we decided we work backwards. So we work backwards from the end application. The end application tells us what is the technical characteristics of the biochar that needs to be. So once we have that end goal in mind, then we work on the machine to see what agricultural waste is available locally and how we can process it in our machine to achieve that quality. So our machine has the capability to control the reaction conditions and hence control the quality of the biochar produced. So it's a matter of titrating that essentially in the machine and controlling and producing the char, doing some experiments and figuring that out. But that's how it is. Say, for example, with activated carbon, there's a certain fixed carbon percentage that they need, volatile matter content that they need, certain ash content that they need. We know it's standard in the industry and we have to achieve that. Otherwise, they're not going to buy it. So we know that target and that's how we work backwards. For example, if solid fuel, so we've been talking to a few cement companies in India that want to see replacement of coal with this carbon-rich material produced from mustard husks, right? And we're trying to explore a pilot with them, and they've given all their technical requirements, including sulfur content that needs to be in the material and things like that. So those end requirements are given to us from the application. We try to work backwards because that gives us a direction. Right. So, so from a carbon emission perspective, overall net carbon emission perspective of our machine, that's something that we're working on a lot. So both on the embodied carbon in making the machine, but also on the carbon emissions that are given out in operating the machine for various applications. And that is netted out against the carbon emissions that are sequestered once the say the biochar is produced, or the carbon emissions that are mitigated in operating in machines. And the idea is to be neutral in that aspect or carbon negative in certain applications such as fertilizers. So on the carbon cycle, definitely we keep a lot of this in mind. And even in the design of the machine, from a design from manufacturing perspective, we are considering a lot of things on how to minimize material wastage in the machine, and how to minimize the number of amount of time and energy intakes in making the machine. And we are sensitive about a lot of the materials that go in the machine that can be polluting, right? So for example, we need an insulation in the machine. It's hot, right? We need to insulate it so that the heat doesn't, we're able to utilize the heat as much as possible. Obviously, we can use some standard insulating materials that are used in labs, for example, glass wool, right? But I mean, what happens to glass wool once it's used in the village? The people are going to throw it, right? And how are they going to use it? And how is it going to be recycled and things like that? So we're not using glass wool at all in our machine, for example. We're just using air as an insulator and creating a chamber with just air as an insulator and keeping it as simple as that. So these are some of the things that we're definitely considering.
We will have only one question. Okay.
I know that question, and I want to ask my question.
Please have him have some hot cup of tea before.
So there is one question is that what is the price at which how much value addition?
Okay, so raw biomass depends on which raw biomass you're considering. So rice straw will be available anywhere between 1.5 to 2 rupees a kg. Rice husks can be available close to 6 rupees a kg. Coconut shells can go as high as 15 rupees a kg. Some really nascent agricultural value chains where biomass usage is not happening, farmers might just give away that agricultural waste for free also. Right, but the more and more demand for that increases, farmers begin to realize that there is value to it and they begin to price that also. So yeah, it depends on which agricultural waste that you're targeting. And the second question was, yes, the value addition from activated carbon, right? So basically, you can consider a um, so typically, if you 1/3, if you put in 100 kgs, 1/3 of that gets converted to charcoal, 1/3 of that further gets converted to activated carbon. So minimum minimum 9 times you have a value addition, right? And then you have a certain margin over and above that you have to add to meet for all the costs.
The real value add will actually happen when you mix nutrients with it. I don't know at what price that sells.
Question which I could have asked you, but I think here, I'm trying to understand your transition from a master's to an entrepreneur. What I remember you mentioned is in the lab you had a protocol of thing which pages. So you probably had contributed to designing the machine which was converting to pages of biomass. And then you said you studied the end product of what it is creating. Now, from here to create a machine which is going to be used, how much of this you're learning in the lab you have taken there, how much you have to learn more, and how much you have to unlearn whatever you had learned till then. So just if you can give a
Yeah, I think in university and working in the lab, that was useful to me in understanding the science of it and just get.
part of the mechanical engineering part of the science or the material part of the science?
So I mean, if
Chemical engineering,
I think
involved
this-
in in putrefaction.
so, actually, this was. I mean, from mechanical engineering, I guess. I mean, it's a very broad field. So a lot on the thermal side of things. Yeah. So I mean, the design of the rig was there that we had in the lab, but that was sponsored by industry according to what their requirements was and was for a European context. Perfectly not suitable to be applied for India, but at least I got a feel for what what that science meant. So right, otherwise it was just in books. So that's what I learned about it in the lab. But when I started going to the field, I saw, okay, fine, the science is valid, but the design of the machine is not going to work at all. What's designed as a lab rig, that same design is not going to work in India at all, right? So the design of the reactor had to completely change as to how we are going to heat the biomass. What should be the nature of the reactor? Should it be a batch reactor, continuous reactor? Should it be multiple hearth furnace? Should it be a fluidized bed reactor? Should it be a screw conveyor? Should it be a tumble dryer sort of a thing, right? So the various design choices that came out of the functional requirements, and that those came out of the needs of the end user that we narrowed down. And there's a lot of trade-offs that were going on. So that had to completely change. How we heated the biomass completely changed. The sizing of the reactor completely changed. Uh, and the entire approach to designing the reactor completely changed. In the university, we were focused a lot on doing modeling simulations and trying to understand how the reactor is going to behave, and then doing experiments and try to improve the model in a small rig by getting data from that. That was valid for that because I was sponsored by an industry partner that wanted to build a really large plant, and obviously you can't build a really large plant and then experimentally validate that. But for our case, we learned we're building a small machine. The machine will fit here, right? And the cost that it takes to manufacture in India, I can just build a machine and test it out, put sensors on it, and get real-time data on it, and actually learn what is working and what is not working out, instead of doing modeling and simulations on it. And only do modeling and simulations for things that I cannot see, right? For things like temperature distribution within the reactor uh, or other things. But for things that I can see and feel, it's just cheaper. It was just cheaper and faster to do it experimentally and actually get much more accurate data than what a model would give. So the approach also changed. Um, And I think other things that changed was earlier it was only technical in nature. Now it was about also, I mean, I need to get money to sustain all this R&D. So where do I get that from? So I think that took, I think 60% of my time just getting that because it takes money to do that. So me and my co-founder just very aggressive about raising money to do this. Otherwise, it's just not possible. And yeah, and
Vidyut is very smart. He doesn't want to touch the last part of your question, the unlearning part, because there are many students here who are who don't want to know how much unlearning will happen when they get out. So I think we should close here. And Vidyut has taken an early morning flight, so he's tired. He's been talking the whole day. So give him a break. I'd like to, join me in acknowledging Vidyut and give him a thunderous applause. I really hope that this talk was really meant for students here. I hope that this has shown that, what we talk about after you graduate, joining a company is not necessarily the only way to make your career. Here is a perfect example of somebody who I'm sure gave away a lot of lucrative jobs and chose to follow his passion, follow his heart, and actually made some great, not only a great enterprise, but also showed examples. And I hope that, I really feel that India's future is fantastic if we get many of you becoming the next Vidyut Mohans in the future. So Vidyut, this is a little token of appreciation from us. And okay, he needs to take a picture. As you remember where you went, this is our main building of NCL.
Painted by,
Wow, we also have scientists who are artists.
and this is.
And since we are talking of sustainability, I know you will not be able to carry this, but we'll ship it to you. Okay. So this pot is made out of recycled PP kits that came out with Oh, wow. So we will certainly ship that to you.
We can ship everything.
Thank you so much.
Thank you
For being here. And I hope there is a good cup of tea waiting for all of us outside. Fantastic.